So here in example 2, we have a population that consists of infinite number of 1s, 3s, 5s, and 7s, all equally likely. So here is the probability distribution of that population. So 1, 3, 5, and 7 are the different x values. They each have probability 1/4. So we're going to actually form the sampling distribution for this population. So first of all, they want us to find all the 2-element samples, the means of those samples, and the probability of each sample. So our samples here, all the samples that start with 1, we could pick a 1 followed by another 1, or a 1 followed by a 3, or a 1 followed by a 5, or a 1 followed by a 7. Or we could pick a 3 followed by 1, 3, 3, 3, 5, 3, 7, 5, 1, 5, 3, 5, 5, 5, 7, etc. So we got 16 samples total, 4 first choices, 4 second choices. Now figure the means of those samples. So just average 1 and 1, you get 1. 1 plus 3 is 4, divide by 2 is 2. 1 and 5 is 6, divide by 2 is 3. 1 and 7 is 8, divide by 2 is 4. And then the probability of each one of these samples, again, there are 16 samples here. So each one of those, since the first and second elements are equally likely, those samples will be equally likely. They'll each have 1/16th chance of being chosen. So 1/16th all the way down. So then what we want to do now to form this sampling distribution is find the probabilities of each one of those sample means. So a 1 occurs here one time out of 16. So sample mean of 1. Oh, and our sample means are 1, 2, 3, 4, 5, 6, and then 7's the highest. So probability that you would get a sample with mean of 1 is 1/16th. Probability that you have a sample with mean 2, you've got 2 there and a 2 there, so 2 out of 16. I'm not going to reduce fractions. 3's, so we got 1, 2, 3, 3 out of 16. And then 4's, 1, 2, 3, 4, 4 out of 16. 5's, 1, 2, 3 5's out of 16 different sample means. 6's, we got 1, 2 out of 16. And then only one sample here has mean 7 out of 16. Now notice that the sum of all those probabilities is 16 out of 16 or 1. That always has to happen. Like it did up here, 4 1/4s give you a sum of 1. And so that is the probability distribution there. This is the probability distribution of x bar. So that's part A. Actually part B, I guess. Yeah. So this is part A here. And part B. And then C, construct a histogram for part B. So we just want to graph this distribution here. So on the vertical, we are going to have our relative frequency. And on the horizontal, we're going to have our samples here. So we've got sample means. So this is our x bar. And then this is probability of x bar. And those probabilities go from 1/16th up to 4/16th. So this would be 0, 1, 2, 3, 4/16ths. And then our samples here, 1, 2, 3, 4, 5, 6, and 7 for x bar. And so the sample mean of 1 has a probability of 1/16, so we're going to put a bar of height 1/16 over that. And then 2 has a probability of 2/16, so a bar up to height 2/16. Over 3, we've got 3/16. So a bar centered on 3/16 height. 4 has a probability of 4/16. Now try to make my bars all have the same width here. And then 3, 2, and 1/16 for 5, 6, 7. So this will be 3 and, whoops, made that one 2. So this one will be 3 and 2 and 1/16. So we get this sort of tent-shaped distribution. So if you draw the curve that goes through the middles of the bars, it's actually a triangle here. So that's a tent distribution is what they call that. So not normal, it's not bell-shaped, but at least it is symmetric. So it's what we call a tent, and it is symmetric. And then what is the probability that x bar is greater than 3.5? So probability that x bar, the mean, is greater than 3.5. So let's see, this is part C. And then part D, we want probability that x bar is greater than 3.5. Well, if x bar is greater than 3.5, it has to be 4, 5, 6, or 7 because it only got whole number values. So this is saying probability x equals 4 or 5 or 6 or 7. So or probabilities, we're going to add together the probabilities. So 4, 5, 6, 7 be 4/16 plus 3/16 plus 2/16 plus 1/16. So let's see, 7, 8, 9, 10/16 or 5/8. And then part E, find mu, the expected value of the x, the random variable x, the parent distribution, and then mu sub x bar, the expected value of the sampling, the random variable for the sample mean. So the x bar distribution, the mean of the x bar distribution. So remember here that mu, which is expected value of x, is the sum of x times probability of x. So I added my x p of x column here, so we just need to multiply across and then sum of. So 1 times 1/4, 1/4, 3 times 1/4, 3/4, 5 times 1/4, 5/4, and 7 times 1/4, 7/4. And if we add those up, 12, 13, 16/4, which is 4. And in fact, if you average these values here, 1 plus 3 plus 5 plus 7, and divide by 4, you get 4. So just a note here, mu is also 1 plus 3 plus 5 plus 7 divided by 4 is 16/4 or 4. Now for the x bar distribution here, we'll notice that 4 is in the middle of the distribution and symmetric on both sides. So we'd expect to have a mean of 4 there also. Well, I added the x bar probability of x bar column, and this guy is going to be the sum of x bar probability of x bar. So this is our mu, and then down here this sum is going to be mu sub x bar. So we multiply straight across, so 1 times 1/16, 1/16, 2 times 2/16, 4/16, going to keep that common denominator. 3 times 3, 16ths, 9 16ths. 4 times 4, 16 16ths. 5 times 3, 15 16ths. 6 times 2, 12 16ths. And 7 times 1, 7 16ths. And if we add this up, we get 64 16ths, which is indeed equal to 4. 16 goes into 64 4 times. So notice here that our mu of x bar, which is the sum of x bar probability of x, is the same as mu, the parent distribution. And that is one of the properties of sampling distributions. And we'll put that to work later. So this is just forming the sampling distribution, finding probabilities with it, finding the mean of the sampling distribution, showing it's the same as the mean of the parent distribution. When that happens, we say that x bar, the sample mean, is an unbiased estimator of the population mean. And then just one note to finish this up here. This process that we did for the sample mean, we could do the same thing here for the sample median, or for the variance, or for the sample proportion. So we'd get a sampling distribution for the median, or for the variance, or for the sample proportion. Similar idea, except a different characteristic.